Hey everyone, and welcome back. I am absolutely thrilled you're joining us today. A huge thank you to Forge College for sponsoring this explainer. So if you remember our last lesson, overview of state models in the EVM and SVM, we took a pretty massive grand tour of how data is represented and figured out where all that data actually lives. But today? Well, today is where things get truly exciting. We're going to translate that kind of abstract idea of state into a concrete, moving, breathing engineering blueprint. Grab your drafting pens, folks, because we are diving into state transitions and execution semantics. We're going to learn exactly how the machine safely alters all that data under the hood. Let's look at the table of contents for today's blueprint. We'll start with an intro to state transitions, then look at journals and checkpoints explained. Next, we'll ground things with the token transfer example, before getting into ordering and atomicity rules, failures and system determinism, and finally, key takeaways and next steps. Think of this as our bridge from the theory of state models into the actual mechanics of execution.
Okay, Section 1, Intro to State Transitions. We know where the data is stored, right? But now we really need to understand the journey. How exactly do we take a blockchain from state A to state B without totally tearing the fabric of the network apart? Simply put, a state transition is just the concrete sequence of writes and updates that turn one official canonical state into another. Think of it like a master architect drafting a blueprint. You don't just magically snap your fingers and have a finished building. You have a very specific, ordered sequence of structural changes. You draft it up, you review it, and then, finally, you stamp it for official construction. In Web3, a high-level operation like transferring a token mutates the state completely differently depending on if you're in the EVM, dealing with entity address storage, or the SVM, dealing with program-managed accounts. But the core concept? It stays exactly the same. It is the journey from one canonical state to the next.
Moving on to Section 2, Journals and Checkpoints Explained. To really wrap our heads around this journey, we need a solid mental model. So let me introduce you to the core concept for today's explainer, the sandbox and the vault. Picture this. On one side, we have the execution journal. This is your transient sandbox. It's basically a chaotic scratchpad. Imagine a developer furiously sketching out transaction drafts in temporary bright orange ink. When your program reads values, computes new balances, makes tentative updates, all of that happens right here. These stage changes are completely invisible to the outside world. Then, on the other side, we have the checkpoint. This is the permanent vault. When a transaction actually succeeds, all those messy orange ink drafts are taken, formalized, and stamped in permanent dark green ink directly into the canonical vault. Boom, it's official. The journal is transient, the checkpoint is forever. Now, here's the kicker. Not all updates inside our sandbox are created equal. We actually have two very different types going on. First up, application-level rights. These are your messy drafts, your token balances, your contract data, all that good stuff. If something goes wrong, these can literally just be tossed right into the shredder, rolled back completely like they never even happened. But second, we have protocol-level bookkeeping. This is stuff like your gas consumption in the EVM or your nonce increments. Let me tell you, even if your transaction completely crashes and burns, this protocol-level bookkeeping is permanently etched into the vault no matter what. The blockchain always gets its fee. All right, Section 3, the token transfer example. Let's see how this all builds together by looking at a highly relatable, concrete scenario. We need to ground these abstract rules, so let's send some money. Here is the 4-step sequence of a standard token transfer. Step 1, the runtime checks all the preconditions and reads the current balances. Step 2, we compute the brand new values. Step 3, we write those tentative updates to the execution journal. Now remember, at this exact stage, it is just an orange ink draft. Nobody else on the network can see this updated balance yet. And finally, step 4, if all the preconditions are met and the execution actually finishes successfully, we commit to canonical storage. That's your permanent dark green stamp. The event is logged and the block-level log records the transfer for the rest of time. What's really fascinating here is how our two architectural heavyweights handle this exact same 4-step process so differently. In the EVM, when the transfer code runs, it stages SST or opcodes. It's basically queuing up writes to specific storage slots inside the smart contract's execution environment. But over in the SVM, it's a totally different flavor. You explicitly pass the accounts into the program, and the SVM directly mutates the byte arrays of those token accounts. It records these writes in a change set, and upon commit, the runtime applies those changes directly to the account stores. So it's the exact same logical transition, but totally different storage behaviors under the hood. Moving to Section 4, Ordering and Atomicity Rules. Now that we understand how the drafts are written, we really need to talk about the strict rules that govern our execution sandbox. Which naturally leads us to a very, very important question. What happens if execution fails midway? Like, what happens when a transaction trips over its own shoelaces, realizes halfway through that it doesn't have enough funds, and just faceplants right in the middle of a draft?
This table brilliantly illustrates the answer. Let's focus first on atomicity. Atomicity just means either all your application level changes happen or absolutely none of them do. It's all or nothing. Both the EVM and SVM offer this transaction-level atomicity. But take a look at the row for visible side effects on failure. If that faceplant happens in the EVM, it preserves gas consumption and nonce changes. Your transaction reverts, sure, but you still pay for the computational effort. In the SVM, the program rights are tossed out, but fees and certain account validation effects, like temporary rent flags, can actually persist. So they both fiercely protect the canonical state, but they leave slightly different footprints behind when they fail.
Section 5. Failures and system determinism. Let's shift our focus to those catastrophic failures. Why is it that when your specific smart contract transaction crashes, the entire global blockchain system doesn't just crash right along with it?
Well, it all comes down to failure isolation. If a revert happens in the EVM, that execution journal goes straight into the shredder. The application state is wiped perfectly clean, almost as if your draft never even existed in the first place. But, as we mentioned earlier, that protocol fee, still consumed. The SVM behaves pretty similarly. In-flight program rights are immediately discarded. However, because accounts are first-class citizens in the SVM, the runtime actually has to do a little bit of reconciliation. It checks rent counters and account LAMP ports just to ensure the system layer remains perfectly consistent, even if your application layer decided to throw a massive tantrum. And all of this brings us to the absolute holy grail of blockchain engineering, determinism. Determinism is the ironclad guarantee that replaying the exact same inputs against the exact same starting state will produce the exact same journal and the exact same commit or rollback outcome every single time. This is exactly why we need these incredibly strict sandbox rules. Validators across the globe, literally thousands of them, must be able to replay the exact same failure path your transaction took, trip over the exact same shoelaces, and arrive at the identical resulting state. If even one validator gets a different result, consensus breaks. Total chaos. Determinism is quite literally the glue holding the vault together.
All right, Section 6, Key Takeaways and Next Steps. We have covered some incredible ground today, moving from abstract ideas into the gritty, real-world mechanics of execution. So let's wrap up the explainer and get you prepared for your homework and the next module. Here are your 3 core principles to walk away with today. Number 1. Always separate transient application rights from permanent protocol bookkeeping in your head. Number 2, read and write ordering builds your staged journal. The literal order of your code dictates the final committed state. And number 3, determinism is everything. It limits hidden mutable states so thousands of nodes can agree on the exact same outcome without fail. Truly, separating the transient sandbox from the permanent vault is your master key to understanding Web3 execution. And now, for your homework. Yes, I'm giving you homework. I want you to do a trace checkpoint exercise. Grab some paper, sketch out the reads and writes for a really simple transaction. Explicitly annotate what goes into the temporary execution journal and what is permanent, protocol-level bookkeeping. Mark exactly where a revert would cut off your journal. Doing this little exercise will perfectly prepare you for our upcoming lesson on storage mechanisms. Before we go, I want to leave you with this final, provocative thought to ponder. If your transaction journal burns in the sandbox during a revert, what hidden dependencies did your application leave behind? What side effects actually survived the fire? Thinking deeply about that is what will make you a truly elite Web3 developer. Thank you all so much for watching and learning with me today. To dive even deeper into this subject and explore a wealth of other amazing Web3 topics, make sure you head over and visit forge.college. Keep exploring, keep building, and I will see you in the next explainer.